All right, let's get started. Okay. So when we were messing with limits on the very first exam, we ran across a form called the indeterminate form. And that form was given as 0 over 0 or infinity over infinity. So if we come across an indeterminate form and can't find the limit by normal means, then we could use something called L'Hopital's rule, not Al Hospital's, okay? So we can use L'Hopital's to fix it. So what L'Hopital says is that if you come across an indeterminate form of 0 over 0 or infinity over infinity, then you can take the derivative separately of the numerator and denominator until the limit exists. So it says the limit as x approaches a of f of x over g of x is the same as the limit as x approaches a of f prime of x over g prime of x. Okay, so if you ever run across an indeterminate form, you can use L'Hopital's. And if it's indeterminate again, you'll use L'Hopital's again. Now, remember, don't get confused with indeterminate and undefined. If you ever run into 1 over 0, then that is not indeterminate, that's undefined, and we cannot use L'Hopital's on that. So L'Hopital's can only be used on 0 over 0 or infinity over infinity. Okay, so what we're looking for is indeterminate forms. And L'Hopital's is also valid for one-sided limits and limits at infinity. Okay, so let's go ahead and try it out. Example 1. Find the limits using L'Hopital's rule. Okay, so the very first thing we're going to do is plug the number in. That's what we're always going to start with. We're going to plug the number in. So if we plug in the limit as x approaches 1, you'll get the natural log of 1 over 1 minus 1. And what is the natural log of 1?
0.
Yay, 0 over 0. So we get an indeterminate form, which means that we can go ahead and use L'Hopital's. So we have to fix this limit. We want to find the limit. So what I like to say is we take them to the hospital. So we use L'Hopital's rule. And now what we're going to do is take the derivative of the numerator and take the derivative of the denominator separately. No quotient rule here. So you'd get the limit as x approaches 1 of 1 over x over 1. And then clean it up. This would become the limit as x approaches 1 of 1 over x, where we now want to plug in 1 to see if everything works out okay. So here you'll get 1 over 1, which means our limit is just 1. Okay, and that's how L'Hopital's works. So if you come across an indeterminate form, then we can go ahead and use L'Hopital's method. You take the derivative of the numerator, you take the derivative of the denominator separately, simplify it, plug the limit in again, and if you run across another indeterminate form, then you keep using L'Hopital's until we get an answer. Any questions on that one? Yeah, where's everybody at today? All right. 2, let's try it again. The limit as x approaches infinity of e to the x over x squared. Well, this, if you plug the limit in, you'll get e to the infinite power over infinity squared. Well, e to the infinite power is just infinity, and infinity squared is still infinity. So again, we run across an indeterminate form, which means we get to take them to the hospital. So we get to use L'Hôpital's, and you take, again, you take the derivative of the numerator and the denominator separately. So you'll have the limit, as x approaches infinity of e to the x over 2x. Okay, so we took the derivative of the numerator and denominator. Now again, plug in infinity. You'll get e to the infinite power over 2 times infinity, which is still infinity over infinity. So again, we get another indeterminate form, which means if we keep getting indeterminate, we keep using L'Hôpital's. So the limit as x approaches infinity, and now from the last step, we again take the derivative of the numerator and denominator separately. So you'll get e to the x over 2. Plug in your limit, e to the infinite power over 2 just becomes infinity over 2, which will leave us with infinity. Okay. So that's how L'Hôpital's works. Any questions on that first page?
Seems easy enough.
For now, right?
Yeah, always for now.
Always for now. Okay, let's keep going then. All right. 3. Same thing. Zoom in, zoom, zoom, zoom. There we go. Always plug in the number first. And we have green now, so you'll get the natural log of infinity over the cube root of infinity. And the natural log of infinity is infinity. And the cube root of infinity is also infinity. So again, you get your indeterminate form. Okay, which means take them to the hospital. So we take the derivative of the numerator and denominator separately. So you'll get the limit as x approaches infinity of 1 over x over, and remember that the cube root of x is the same as x to the 1/3. So this will become 1/3 x to the negative 2/3. Okay, and definitely some cleanup. So you'll get the limit as x approaches infinity of 1 over x over, and I'm going to rewrite the denominator as 1 over 3x to the positive 2/3. Okay, so now we have fraction over a fraction. So we'll multiply by the reciprocal. And we'll have 1 over x times 3x to the 2/3 over 1. Simplify again, and you get the limit as x approaches infinity, and then 1 over x times 3x to the 2/3. You'll subtract 2/3 minus 1. So this means that we are going to get 3 over x to the 1/3. 3 over x to the 1/3. Okay. And now, if you plug in that limit, you'll have 3 over infinity to the 1/3. So this denominator is getting larger and larger and larger, but of course at a slower rate because it's to the 1/3 power. But remember that this limit, let's just say this limit looks like the power limit we've seen before. The limit as x approaches infinity of 1/x to any power of n will always equal what number?
0.
0. Good. So that means if I were to rewrite this, I mean, it doesn't matter what number is in the numerator, but if I rewrote it as 3 times 1/infinity to the 1/3, we know that this would become 0. So the whole answer is just what?
0.
0. There you go. So this just becomes 0. Because this part becomes 0. Oof. All right. Any questions on that one? Okay. Again. All right. 4. The limit as x approaches 0 of tangent x minus x over x cubed, and plug it in, you would get tangent at 0 minus 0 over 0 cubed. What is the value of tangent at 0?
You know, 1 or
Close. Tangent at 0 is
0.
0. So you get 0 over 0, which gives us indeterminate. Okay, so we take him to the hospital, which means you take the derivative of the numerator and denominator separately. And what is the derivative of tangent?
Secant squared.
Secant squared x minus 1 over 3x squared. Okay, and then from here, you can plug in 0 again. You'd get secant squared of 0 minus 1 over 3 times 0 squared. What is the value of secant at 0? I guess to make it easier, what is the secant is the reciprocal of what function?
Cosine.
Cosine. What is cosine at 0?
1.
What's the reciprocal of 1?
1.
And what's 1 squared?
1.
Good. So you get 1 minus 1 over 0, which leaves us with 0 over 0. Gross, which is indeterminate. So we take them to the hospital again. The limit as x approaches 0. And now we need the derivative of secant squared. Ooh la la. So if you have d over dx, and I'm going to rewrite it as secant x squared, well, we're going to have to chain rule this. So you'll get 2 times secant x. That's the derivative of the outside. And what is the derivative of secant? Anybody?
Give me 10 seconds. I'm gonna grab my paper.
Secant x times tan x.
Secant x, tangent x. So this becomes 2 secant squared x tangent x. Okay. So that's what goes here. 2 secant squared x tangent x over 6x. So 2 secant squared x tangent x 6x. Okay. And now you can plug in 0 again. And let's see what happens. Okay, so we learned that secant squared at 0 is what value?
1.
1. And tangent at 0 is
0.
0. So all of this is still going to be what?
Indeterminate. 0 over 0.
Indeterminate. Oh my goodness. Oh, which means that we could use L'Hopital's again, but it can get messy because now you're going to have to use what rule on this numerator?
Product.
Product.
Rule.
Product and a chain for that secant squared again, right? But to avoid that, does anybody remember your trig limit identities? So we don't have to keep going further down the rabbit hole. What is the limit as x approaches 0 of tangent x over x? What number does that equal?
Is that 1?
That's 1. Do you see anything like that in this problem of that form?
Could you multiply the top and the bottom? Oh.
We could, but this is set up
factor it out?
nice. This is set up nicely to where we don't have to multiply by anything. We can separate it because the whole numerator is connected by what?
Multiplication.
Multiplication. So I can separate this by saying the limit as x approaches 0 of 2 secant squared x over 6 times the limit as x approaches 0 of tangent x over x. Ah, have we done anything wrong? Not that we think, that, right? Which means, where is this limit going? Or what is it going to become?
A 1.
A 1. So this becomes 1. And what we're left with is the limit as x approaches 0 of 1. I'll just make that. Yeah, why not? I can make that 1/3 secant squared x. And now you plug in 0 and you get 1/3 times secant squared at 0, which we learned again that secant squared at 0 is what value?
1.
1. So what's our answer?
1/3.
1/3. My goodness.
So you just didn't take the derivative again. You just separated it.
Exactly. If we notice that we can fix it by using prior techniques, then why not do that than having to take the derivative again and deal with the chain product rule of trig functions? which brings me back to the first step. If you guys remembered your trig identities from pre-cal, we would have been done a long time ago. Anybody remember what secant squared minus 1 is?
Tangent squared.
Oh, thanks, guys. Secant squared minus 1 is tangent squared x. And we can split this guy up, right? You can split him up as the limit as x approaches 0 of 1/3. Actually, yeah, just take that 1/3 out and I can rewrite this as tangent x over x squared. And once again, as this limit goes to 0, what number is tangent x over x going to?
One.
That goes to 1. So that means we're left with 1/3 times 1 squared. Bam. Oh, identities. Crazy, right? All right. Any questions on that? Okay. 5. Once again, plug the number in first. The limit as x approaches pi from the left, you're going to get sine of pi over 1 minus the cosine of pi. What is the value of sine at pi?
0.
0. What is the value of cosine at pi?
-1.
-1. You get 0 over 2, which is
0.
0. No L'Hopital's needed. My goodness. Okay. Any questions on that page? Everybody's got a case of the Mondays, huh? Okay. So next part of L'Hopital's deals with something called indeterminate products. If the limit as x approaches f, x approaches a of f of x is 0, and the limit as x approaches a of g of x is infinity, then it is unclear what the value of the limit of f of x times g of x will be. This kind of limit is called an indeterminate form of 0 times infinity. So remember, 0 times infinity is not 0. 0 times infinity is indeterminate. And the way we deal with this is by rewriting the product of f and g as a quotient. So you have two options. You can rewrite f times g as f over 1 over g, or you can rewrite it as g over 1 over f. Okay. And we rewrite it as an indeterminate quotient. And then we see if we can find the limit that way. And if not, we use L'Hopital's. Okay. And now when rewriting as an indeterminate form, as a quotient, you want to be smart about what function to put in the denominator. So for this next problem, we have the limit as x approaches 0 from the right of x times the natural log of x. Of course, let's go ahead and plug in 0 just to see what happens first, like always. So if we do that, you'd get 0 times the natural log of 0. I guess I could say 0 from the right. And this would give me 0. Whoops, that's supposed to not be there. Whoops, there we go. Of 0 from the right times the natural log of 0 from the right. So you get 0 times, and the natural log, as you approach 0 from the right, is headed towards where? If you approach 0 from the right side, where are your y values headed?
Negative infinity.
Negative infinity. And 0 times negative infinity is unfortunately indeterminate. So let's go ahead and rewrite it as a quotient. So for this problem and for any problem, it's always smart to keep the natural log in the numerator and put anything else in the denominator. If you put the natural log in the denominator, it's gonna be a long process. So when we rewrite this, we're gonna have the limit as x approaches 0 from the right of the natural log of x over 1 over x. So we have just rewritten it as a quotient. And now just to clean it up, you get the natural log as x approaches 0 from the right of the natural log of x over x to the negative 1. Okay. And if you were to plug in 0 again, well, you would end up with, I believe, negative infinity over infinity, which again would give us indeterminate. Maybe be, because 1 over x, let me see. 1 over x looks like that. And if you approach 0 from the right, yeah, you'd be headed towards infinity. So good, we get an indeterminate form, which means now we get to use L'Hopital's. Take them to the hospital. So the limit as x approaches 0 from the right, and we're taking the derivative of the numerator and denominator separately, which means that derivative of natural log is 1 over x, and the derivative of x to negative 1, negative x to the negative 2. Okay, now we have some cleaning up to do. The limit as x approaches 0 from the right of 1 over x over negative 1 over x squared. So we're just rewriting everything, and then we'll multiply by the reciprocal. Of 1 over x times negative x squared over 1. Reduce, and we'll get negative x. And now, what happens if you plug in 0?
You get 0.
You get 0. All of that work for 0. So rewarding though, right?
Oh yeah, so rewarding.
Very rewarding. Okay. Cool. So that is an indeterminate product. So again, if you run across 0 times infinity, rewrite it as a quotient. Okay. Next is an indeterminate difference. If you have the limit as x approaches a of f of x minus g of x, where f of x becomes infinity and g of x becomes infinity, then you come across the indeterminate form of infinity minus infinity. To evaluate this, or to simplify it, we will turn it into one whole fraction by getting common denominators, rationalizing, or factoring whatever we need to do. Okay. So let's go ahead and check number 7 out. You have the limit as x approaches pi over 2 from the left of secant x minus tangent x. Okay. So if you plug in pi over 2, you get secant of pi over 2 from the left minus the tangent of pi over 2 from the left. Okay. So for this one, well, secant, remember, looks something like this. And it would have a vertical asymptote at pi over 2. So for secant, if you approach pi over 2 from the left, where are your y values headed?
Infinity.
Infinity. And then tangent looks like this. Where again, you have another asymptote at pi over 2. And if you approach pi over 2 from the left, where are your y values headed again?
Infinity.
Infinity. And you get infinity minus infinity, which is going to be what?
Zero.
0. Get out of my class. Indeterminate. All right, good. So that means we have to fix it. We will rewrite it. And this will become the limit as x approaches pi over 2 from the left. And now we have to think of identities. Secant can be rewritten as what identity?
Is it tangent squared plus 1?
Well, we're not doing any derivatives yet. We are rewriting because we have to rewrite it before we do any derivatives.
Is it
So
1 over
secant-
About the
cosine?
identities, like the trigonometric.
1 over cosine, right? So trig
Oh, see,
identities.
I'm sorry. Yes.
You're good. And tangent is what? What's another way to rewrite tangent using trig identities?
Sine over cosine?
Sine over cosine. Good. And now you notice that these two fractions have the same what?
Denominator.
Denominator. Good. Which becomes 1 minus sine x over cosine x. Okay. And of course, if you were to plug pi over 2 into this, I guess we could show it. Why not? Because all we've done is combine the fractions together. And if I plug pi over 2 in now, I get 1 minus sine of pi over 2 over the cosine of pi over 2. And this would give me 1 minus 1 over 0. So you'd get 0 over 0, which is indeterminate. Which means we get to take it to the hospital. We use L'Hopital's, and now we take the derivative of the numerator and denominator separately. So I get the limit as x approaches pi over 2 from the left. And what is the derivative of 1 minus sine x?
Cosine.
Will it be negative? Right?
Yeah, negative cosine x.
And then what's the derivative of cosine?
Negative sine.
Negative sine x. So this will give me the limit as x approaches pi over 2 from the left of positive cosine over sine, or what other function is that?
Cotangent.
Cotangent. I'll leave it actually. It's cotangent, but we'll get there in a second. So you have cosine x over sine x. And now if I plug in pi over 2, what is cosine at pi over 2?
0.
What's sine at pi over 2?
1.
1. So our answer is
0.
0. Good. Okay. The other route, we can just say that this became the limit as x approached pi over 2 from the left of cotangent x, and cotangent at pi over 2 is also 0. Okay. Any questions on that? So if you have an indeterminate difference, try to put it together by common denominators, rationalizing, factoring, whatever you need to do to put it as one term. Okay. All good? All right. Okay. And then one more form to look for. Indeterminate powers. So if the limit of f of x is 0 and the limit of g of x is 0, an indeterminate power is 0 to the 0th. 2, if the limit of f of x is infinity and g of x is 0, then infinity to the 0th is an indeterminate power. And 3, if f of x is 1 and g of x is plus or minus infinity, then 1 to the infinite power is also an indeterminate power. There is no 4, even though I typed a 4. Rule 4, stuff. No stuff. All right. So if you come across an indeterminate power, the only way to handle this is by using natural logs. So you'll let y equal the limit, and then we'll apply natural logs to both sides, and then fix it by everything we've learned today. So let's go ahead and try this out. Number 8. Of course, we plug in the number first. So we're going to plug in 0. So this would give me 1 plus the sine of 4 times 0, which is just 0, all raised to the cotangent at 0. Okay. Well, the inside becomes 1 plus sine at 0 is 0. And cotangent at 0 is actually undefined. So cotangent at 0 will give me infinity. So this will become 1 to the infinite power, which is indeterminate. And remember, cotangent looks like this. A little weirder. 0 and pi. So that's why we go to infinity. Okay. All right, so again, the way to handle this, let me zoom in, is we're going to say y equals the limit as x approaches 0 from the right of 1 plus the sine of 4x cotangent x. And then we are going to apply natural logs to both sides. So you'll get the natural log of y equal to the limit as x approaches 0 from the right of the natural log of 1 plus the sine of 4x raised to the cotangent of x. And once we apply those logs, we have a lot of cleaning up to do on the right side. So we leave the left side alone for now. So this will become, and by the rules of logs, so the power rule for logs, remember that the power will come down in front of the natural log, or just the log. So you're going to get the limit as x approaches 0 from the right of cotangent x times the natural log of 1 plus the sine of 4x. Okay. And now, even if you plugged in 0 here, this would now be infinity times the natural log of 0, which is negative infinity. So you'd get infinity times infinity, which would still be indeterminate. Or would that just be 0? 1 plus 0. No, sorry. That would be the natural log of 1, which is 0. So you get infinity times 0, which is still indeterminate. Okay, so with that being said, this still has to be fixed. So now you have an indeterminate product, which means we need to rewrite it as a quotient. So again, you want to be smart. You keep the natural log in the numerator and you put anything else in the denominator. So when I rewrite this, I get the limit as x approaches 0 from the right of the natural log of 1 plus the sine of 4x over 1 over cotangent x. Okay, but by identities, trig identities, 1 over cotangent is just what?
Tangent.
Tangent. So you get the natural log of 1 plus the sine of 4x all over tangent x. Okay, and again, if you were to plug in 0 still, you'd end up with the natural log of 1 over the tangent of 0, and you would end up with 0 over 0, which is still indeterminate. I'll leave that there, which means now we L'Hopital's. But any questions on that setup so far? Crazy, right? Okay, so now we L'Hopital's. And I get the limit as x approaches 0 from the right. And again, we take the derivative of the numerator and denominator separately. So this is going to involve a little bit of chain rule. So if you have d over dx of the natural log of 1 plus the sine of 4x, well, remember the chain rule derivative for the natural log is the derivative of the inside over the inside. So what is the derivative of the inside? 1 plus sine 4x.
4 cosine 4x.
Good. Over the same inside, 1 plus the sine of 4x. Good. So that's going down here. 4 cosine 4x over 1 plus sine 4x over, And what is the derivative of tangent?
Secant squared.
Secant squared x. Okay. And of course, some cleaning up to do. Our little fraction trick, this denominator is just going to come down here. So you'd have the limit as x approaches 0 from the right of 4 cosine 4x over, and I'm going to write this as secant squared x times 1 plus the sine of 4x. Okay. Woof. Now, let's plug in 0. Let's hope it works. If not, we're taking that derivative all over again. Of course, if it's indeterminate. So if I plug in 0, I get 4 cosine of 0 over secant squared of 0 times 1 plus the sine of 0. All right. And what is cosine at 0?
1.
1. So that's just 4. What is secant squared at 0?
1.
1. And what is sine at 0?
0.
0. So you end up with 4 over 1 times 1, which is just 4. Okay, but we're not done yet because we still have the left side to deal with. Remember that we had y equals and then the natural log of y equals? Well, we have to bring that back in. Oh, goodness. So this means that we now have, maybe I should draw a little path. Let's see. So now the natural log of y equals 4. And now it's our job to solve for y. So do you guys remember how to get a natural log, how to convert natural log to exponential? If I said natural log base e of x is equal to y, and I say convert to exponential, what would you write? Dun, dun, dun. Remember, it's the base raised to the outside number, and you set it equal to the inside. So what would my exponential function be?
E to the power of y equals x.
That's it. So that's exactly what we're going to use here. So what's our answer?
E to the power of 4.
E to the power of 4 equals,
Y.
that's it. Oh my goodness. That's just, I don't know if it's a lot, maybe. Good times though. Okay, any questions on that one? All right, number 9, same thing. Let's try it. All right. Number 9, the limit as x approaches 0 from the right of x to the x. Again, plug in that 0 and you'd get 0 to the 0th power, which is indeterminate. So we're going to say again, y equals the limit as x approaches 0 from the right of x to the x. And then we apply the natural logs to both sides. And you get natural log y equals the limit as x approaches 0 from the right of the natural log of x to the x. Now remember, by natural log properties, that x will come to the front. So you get the limit as x approaches 0 from the right of x times the natural log of x. And again, if you were to plug in 0, you'd get 0 times the natural log of 0, which is 0 times infinity. All right, then 0 times negative infinity, which is indeterminate. Okay, which means we now have an indeterminate product. So we rewrite as a quotient. So that means that we'll get the limit as x approaches 0 from the right. And again, never put the natural log in the denominator. So we'll have natural log x over 1 over x, which then becomes the limit as x approaches 0 from the right of natural log x over x to the negative 1. And once again, if you plugged in 0, you'd get negative infinity over infinity, which is indeterminate. Which means now we get to L'Hopital's. You get the limit as x approaches 0 from the right, and we're taking the derivative of this fraction, just the numerator and denominator separately. So you'll get 1 over x over negative x to the negative 2. Clean up. X approaches 0 from the right, 1 over x, negative 1 over x squared. Limit as x approaches 0 from the right, multiply by the reciprocal, negative x squared over 1, which will give us the limit as x approaches 0 from the right of negative x. Where now it's safe to plug in 0, so we get 0. But are we done?
No.
No. We now get natural log of y is equal to 0, which means convert it from log to exponential. And what does the conversion become? E to the
Power of 0.
equal to
Equals
y. And what is anything to the power of 0?
1.
1. Boom. All right. Don't forget those ones. Those are definitely test problems. Wink, wink. All right. Any questions on that page?
I do. So
What's
in
that?
that last one, and I guess the one before it, so are we saying that, like on the last one, we're saying 1 equals the limit as x approaches 0 from the right of x to the x power?
Exactly.
Okay. I don't know
Okay.
why that helps me, but it does.
No, that's what we're doing, yeah. And that e to the 4th is the limit of 1 plus sine 4x to cotangent x.
Thank you.
Mhm. All right. Those are all our rules. So the rest here is practice. So speed round. All right. So let's see what we got. Limit as x squared minus 1 over x squared minus x. So if I plug in 1, I get 1 squared minus 1 over 1 squared minus 1, which that's going to give me what?
0 over 0.
0 over 0. Indeterminate L'Hopital's. Do we want to? Yeah, why not? We can L'Hopital's. Or you can actually fix this, because you see the numerator and denominator, you could what? It's fine. We'll do L'Hopital's first. You get the net, the limit as x approaches 1, and you'd get 2x over 2x minus 1. And if you plugged in 1, 2 times 1 over 2 times 1 minus 1, we'd get 2 over 1, so we get 2. All right. But remember that I think this can also factor to x plus 1, x minus 1 over x times x minus 1. And then cancel, and you get x plus 1 over x. And if you plug in 1, you get 2 over 1, which is 2. Okay.
There's too much stuff going on for my brain to go all the way back to factoring.
Yeah, this lesson's long too, I saw.
I mean, I could stop because
Yeah,
we're basically
practice,
done.
more
The rest is just practice problems. So if y'all
No,
are
no.
good, then hey,
No, please go. Please keep going.
then I'm good.
practice. Yeah, I like to practice. They are deadly though. I like how you say hospital. I just imagine them rushing a cosine x to the hospital.
There you go. That's what it's about. All right, cosine pi over 2 over 1 minus the sine of pi over 2. And what's cosine at pi over 2?
-1. I'm sorry, 0.
0.
No,
And
it's
you
pi.
get 1 minus, what's sine at pi over 2?
1.
1. No matter what, that's 0 over 0. Indeterminate. Take them to the hospital. And the limit as x approaches pi over 2 from the right. What's the derivative of cosine?
Negative sin x.
Negative sine x. What's the derivative of the denominator?
Negative cosine.
Negative cosine x. And you get the limit as x approaches pi over 2 from the right. And you would get positive sine x over cosine x, or what function is that?
Tangent.
Tangent of x. Now let's plug it in, and tangent at pi over 2. What is
1.
that?
1.
Hmm.
No?
No, pi over 2, right? So remember that tangent looks like this, and it has vertical asymptotes at what?
Every pi over 2.
Every pi over 2. So if you are approaching pi over 2 from the right, where are we headed?
Negative infinity.
Negative infinity. I mean, I could have kept it as the other form. I should have, just to show you. I mean, there's always another route. So if this was the limit as x approached pi over 2 from the right of positive sine over cosine. you get sine of pi over 2 over the cosine of pi over 2. Well, again, what's sine at pi over 2?
1,
1. And what's cosine at pi over 2?
0. I wasn't mathing right.
0. So 1 over 0, is that indeterminate or undefined?
Undefined.
That's undefined. So that means you couldn't use L'Hopital's again. So from here, you would think of the graph or whip out that handy dandy calculator. Because this is 0, what is that? Cosine at pi over 2 from the right side. Yeah, so that would be a negative 0, which would leave you at negative infinity. So again, there I am thinking of the graph to help us out. And then other than that, you can just do the calculations using your XY charts if you want, or just think of the unit circle, right? Yeah, this is fun. This is always fun. Here's pi over 2, there's 0, there's pi. And if you approach pi over 2 from the right side, remember that all the values are greater than pi over 2, which means you're in this region. And in that region, in that quadrant, cosine is what? Positive or negative?
Negative.
Negative. So that's why I put that negative 0 there. And 1 over negative 0 is negative infinity. All right, stuff to think about, right? All right. Keep going, keep going, keep going. All right. 3. The limit as x approaches 0 of sine 4x over tangent 5x. If you plug in 0, you get sine of 0 over tangent of 0. And what are both of these at 0?
Zero.
0 over 0. Indeterminate. Take them to the hospital. What is the derivative of sine 4x?
Or cosine 4x.
4 cosine 4x. What is the derivative of tangent 5x?
5 secant squared 5x.
Good. 5 secant squared 5x. Plug in 0. Let's see what happens. 4 cosine 0, 5 secant squared 0. And cosine at 0 and secant at 0 are both what value?
1.
1. So our answer is just 4/5. All right. Okay. 4. Ooh la la. Okay. Limit as t approaches 0 of e to the 2t minus 1 over sine t. Plug in 0. E to the 0th minus 1 over the sine of 0. That becomes 1 minus 1 over 0 or 0 over 0. Indeterminate. Okay, so take them to the hospital. And what is the derivative of e to the 2t? So remember, if you have the chain rule derivative, I'll say d over dt of e to the gt, that derivative is g prime of t times e to the gt. So what would the derivative of e to the 2t be?
E to the 2t times 2.
That's it. Or 2e to the 2t over cosine t. Plug in 0. 2e to the 0th over cosine of 0. What's our answer?
2.
2. Good. Everybody good? Oh, I left that on there. Cool. All right. Keep it going. Keep it going. 5. Limit as x approaches pi over 2 of 1 minus sine x over 1 plus cosine 2x. Of course, plug it in first. 1 minus the sine of pi over 2 over 1 plus cosine of 2 times pi over 2. And we know that sine at pi over 2 is 1. And 1 plus, and what is cosine at pi?
-1.
Good, because that becomes cosine of pi. So you get 0 over 1 plus -1, which is 0 over 0. Indeterminate. Okay, take him to the hospital. Limit as x approaches pi over 2. And what's the derivative of your numerator?
Negative cosine x.
Negative cosine x. What's the derivative of your denominator?
Negative 2 sine x.
Negative 2 sine 2x.
Yeah, that.
Yeah. Plug it in and you'll get cosine of pi over 2 over 2 sine, and 2 times pi over 2 is pi, right? And unfortunately, cosine at pi over 2 is what?
Zero.
0. Sine at pi is also
0.
0. So again, we get indeterminate. Oh boy. Take him to the hospital again. Limit as x approaches pi over 2. And what is the derivative of, so that's plus plus. So what's the derivative of cosine?
Negative sine x.
Negative sine x over the derivative of 2 sine 2x.
Or sine 2x
For
or cosine 2x.
cosine 2x. Good. Plug in pi over 2. Two times pi over 2 is pi. And what is the value of sine at pi over 2?
What?
-1. What is the value of cosine at pi?
Also -1.
And you'll get -1 over -4, or
1/4.
1/4. There we go. Yeehaw. All right. Again. Plug in 1. Give 1 to the 8th minus 1 over 1 to the 5th minus 1. That still gives you 0 over 0, which is indeterminate. And then take them to the hospital, and the limit as x approaches 1, derivative of x to the 8th, 8x to the 7th over 5x to the 4th. Reduce, and you'd have, what's that, 8x cubed over 5, plug in 1, and what's our answer?
Eight fifths.
8/5.
8/5.
We could just stick to these, it'll be okay.
Just these ones?
Yeah.
The trig ones are easy. Okay. 7. Again. Plug in 0. E to the 0th minus 1 minus 0 over 0 squared. You get 1 minus 1 over 0. 0 over 0 indeterminate. Okay. Take it to the hospital. The limit as x approaches 0. What is the derivative of the numerator?
E to the x minus 1.
1. Good. Over 2x. If you plug in 0, you get e to the 0th minus 1 over 2 times 0, which is again 0 over 0. L'Hopital's it again, and you'll get the derivative e to the x over 2, plug in 0, and what's our answer?
1/2.
1/2. All right. See, we're moving. Yeehaw. All right. 8. The limit as x approaches infinity of e to the x over 10 over x cubed. Ooh la la. Plug in infinity, and you get e to the infinity over 10 over infinity cubed. Well, infinity over 10 is still infinity. So you get e to the infinite power over infinity. So infinity over infinity. So you get indeterminate. Okay, which means take them to the hospital. And what is the chain rule derivative for e to the x over 10? I guess you can make it simple. What's the derivative of x over 10?
1/10.
1/10. So the numerator becomes 1/10 e to the x over 10 over 3x squared. Where if you plug in infinity, you're still going to get infinity over infinity. Which means L'Hopital's it again. And now, what is the derivative of the numerator going to be?
One over 100.
Good.
E to the x to the power of 10. Or
Good.
x over 10.
Good. Over 6x. But again, if you plug in infinity, you're going to get infinity over infinity. Which means L'Hopital's hopefully one more time. And what's my new derivative of the numerator?
One over 1,000
Yeah.
e to the x over 10.
1 over 1,000 e to the x over 10 over
6.
6. And now if you plug in infinity, you get e to the infinity over 10 over 6, which then becomes 1 over 1,000 e to the infinite power over 6, which just becomes, and you can do this trick again, you can move that denominator down. So it just becomes infinity over 6,000, which is still what?
Infinity.
Infinity. Oh my goodness.
Basically, any of these with infinity and you have a power on the bottom, it's gonna kind of make you do it a lot because the bottom's always gonna, if the top's always infinity and the bottom can't. Basically, you have to get it to 6.
Yeah. So you'd
Yeah.
have to get rid of that x for that one.
Yeah, basically you have to get rid of it. I've noticed that.
Mhm. All right. All right. 9. Oof. Why did I do that one? Okay. So here, plug in 0 again. You get x, not x. You get 0 times 3 to the 0th over 3 to the 0th minus 1. That becomes 0 times 1 over 1 minus 1, which gives you 0 over 0, which is indeterminate. Okay, so that means we're going to take the derivative of the numerator and denominator. But before we do so, remember that the derivative of an exponential function with any base a is a to the x times the natural log of that base a. And then if we are going to take the derivative, what rule are we going to have to use in the numerator?
Product rule.
Product rule. Good. So I'll do that here. F is x, g is 3 to the x, f prime is 1, g prime is 3x natural log 3. Okay. So the numerator becomes 3 to the x plus x 3 to the x natural log 3. X times 3 to the x times the natural log of 3. And then the denominator is just 3 to the x times the natural log of 3. Okay. So now let's just plug in 0 and see what happens. You get 3 to the 0th plus 0 times 3 to the 0th times the natural log of 3 over 3 to the 0th times the natural log of 3. This will become 1 plus 0 over 1 times the natural log of 3. So our answer here is just 1 over the natural log of 3. Good stuff. All right, still going. All right, 10. Limit as x approaches 0 of cosine mx minus cosine nx over x squared. Of course, plug in 0 first. You'd get cosine of 0 minus cosine of 0 over 0 squared. That becomes 1 minus 1 over 0, 0 over 0, which is our indeterminate. Okay, so take it to the hospital. And you get the limit as x approaches 0. Treat m and n as a coefficient or a constant. And what would the chain rule derivative be for cosine mx?
M negative m sine mx.
Good. And then what would the chain rule derivative be for cosine nx?
N sine nx.
Good. Over 2x. Okay. Now let's make that look a little pretty. So you'd have limit as x approaches 0 of negative m sine mx plus n sine nx over 2x. And again, if you plug in 0, you will end up with 0 over 0. So L'Hopital's again. The limit as x approaches 0. And now, what is the chain rule derivative of negative m sine mx?
Negative m squared
Good,
cosine mx.
good. Negative m squared cosine mx plus, what's our chain rule derivative of n sine nx?
N squared cosine nx
Good.
over 2.
Over 2. That was the easy part. Now plug in 0. You get negative m squared cosine 0 plus n squared cosine 0 over 2. And what is cosine at 0?
One.
1. So we get negative m squared plus n squared over 2. Ooh, man. All right. All good?
That was fun.
Yeah, so much fun.
Oh, the good stuff. Oh yeah, Ryan's still there. All right.
He's
Taking all
really
the
earning his paycheck.
I'm taking all the fun. Sorry. All right. 11, plug in 0.
I'm owed it from teaching
Sign with 0.
related rates.
Yeah, there you go. And that's 0 from the right. So that would be 0 times negative infinity, which is indeterminate. So Lopi, nope, not L'Hopital's yet. So we have an indeterminate product. So we now have to rewrite it as a quotient. So we rewrite this. And again, always keep the natural log in the numerator. You have natural log over 1 over sine of x. And then 1 over sine of x becomes what function?
Cosecant. X.
Cosecant x. And again, if you plug in 0, you would still get negative infinity over infinity, which would be indeterminate. Okay, which means we can now L'Hopital's, and the limit as x approaches 0 from the right, the derivative of the natural log is 1 over x. And does anybody know the derivative for cosecant?
Is it negative cosecant x cotangent x?
Very good. Negative cosecant x, cotangent x. Okay, and now cleanup time. So we can have this as the limit as x approaches 0 from the right. And I'll keep this as this for now, 1 over x. And cosecant cotangent x can be written as negative 1 over sine x tangent x. All right. And now we reciprocate. And you have 1 over x times negative sine x tangent x over 1. Okay, almost there. Let's see. Then this will become the limit as x approaches 0 of negative sine x tangent x over x. Okay. So as x approaches 0, this means that we can do one of two things. It doesn't matter how we split it up. Remember our trig limited identities. It says x approaches 0 of sine x over x, or tangent x over x. These both are going to go to what number?
1.
1. So it honestly doesn't matter which one you choose. So let's go ahead and just put with the sine x. Why not? So we'll make this the limit as x approaches 0 from the right of negative sine x over x times the limit as x approaches 0 from the right of tangent x. Well, we know that this limit is going to what number?
-1.
That's going to -1. Good. So this becomes -1 times the tangent at 0. What is tangent at 0?
0.
0. So -1 times 0. And all of this is just 0. So gross, right? Okay. 12. Last one. Cosecant x minus cotangent x. If you plug in 0, you get cosecant of 0 minus cotangent of 0, which I believe is just infinity minus infinity. And then here you get to rewrite it. So no L'Hopital's just yet. The limit as x approaches 0. What's another identity for cosecant? Trig identity.
1 over sine.
1 over sine. And what's another identity for cotangent?
1 over tangent.
Other than that.
Oh, cosine over sine.
There you go. I mean, you're right, but you want to choose a better identity because now you notice that these have the same what?
Denominator.
Denominator. So you get 1 minus cosine x over the sine of x. And even if you plugged in 0 now, you'd get 0 over 0, which is indeterminate. Okay, so now this gets L'Hopital. And the limit as x approaches 0, what is the derivative of the numerator?
Sine of x.
Sine of x, good. Over the derivative of the denominator?
Cosine x.
Cosine.
Cosine x. And now you can plug in 0 to both, or you can rewrite it as tangent x. And what is tangent at 0?
0.
0. And there it is, y'all. L'Hopital's. Breathe it in. All the trig and algebra you can handle. All right, but that finishes that.